Alright guys, so I'm back again with 10.6, and this is how to find segment lengths inside of a circle. Okay, so things get a little bit more tricky here, but not so much because of what you have to do is hard, but because of some of the algebra that's involved when some of these as they get a little bit more complicated. So make sure you're paying attention, and if you need to go back and rewind to kind of see how some of these things work out, don't be afraid to go ahead and do so. Okay, so let's start off with theorem 10.14, which is the segments of a chord's theorem. Basically, this says that the product of the length of the segments of one chord are equal to the product of the other. So if I look at the chord that stretches across the 4 and the 6, that's one chord. And if I look at the other chord is part X and part 3. So if I take that whole chord, 4 times 6, and I set it equal to 3 times X, like that, okay, what this theorem says that if I take the product of 3 and X and set it equal to the product of 4 and 6, that they equal one another. Okay, now they might not look like they do, but they do. Okay, so 3 times X would be 3X equals 24. Okay, and then I divide by 3 and I get X equals 8. Now that seems pretty easy, but the fun comes when they when they give you a problem that looks kind of like this, to where we got a bunch of X's and binomials inside of this. So basically the setup's the same. I look at the whole chord M to L, okay, and the whole chord of K to J, okay, and so I want to take the product of Mn times NL and set it equal to the product of Kn times Nj, and then those are basically, we could say those two chords are equal to each other. So on the left side there I have X plus 1, which is NL, times X plus 2, which is Mn, and I've set that equal to Kn, which is X, times Nj, which is X plus 4. Now on the left side, remember I said it was a little bit tricky. You have to do kind of some foiling here, or mass distribution, or binomial product here, and so you got to go X times X plus 2, and then 1 times X plus 2, and then combine like terms, and then just distribute X times X plus 4 on the right there, and you're going to end up with X squared plus 3X plus 2 on the left, and X squared plus 4X on the right. And now all it is a matter of combining like terms. So as I start to combine like terms, the X squareds cancel each other out. Minus 3X over the right side, and I get 1X equals 2. Okay, so just look at that for a moment, and remember how to combine like terms and move things around, and you'll see that it's really not all that bad because the X squareds cancel each other out. Okay, just remember you're gonna have to use a little bit of foiling here. Okay, all right. Now let's go on to the next slide here. Now, theorem 10.15 is the segments of secants theorem. So last one dealt with chords, and this next one is going to deal with secants. So basically this one says that the product of the external segment and the full secant segment is equal to the other product of the external times the full. So what does all that mean? Okay, so external segment, guys, is the piece from the vertex of that angle, okay, to where now you see that vertex of that angle is outside the circle, okay, but as that top part of that angle where the 6 is, the external segment is from the vertices to the edge of the circle on the outside, okay, and then the other external segment would be the vertices of the angle to the outside of the circle, which is a measurement of 5. That's the external segment. So the 6 and the 5 are the external segments, okay, and then the full secant, okay, on the top one, the full secant is 9 plus 6, which is 15, but then on the bottom we cannot combine X and 5 together through simple addition, and so, or through combining like the rules of combining like terms, so all we have to leave it as is X plus 5. And so when you set this up, it looks kind of like this. Okay, the 6 is the external segment times the full length of the secant, which is 9 plus 6, which is 15. So that's where the 6 times 15 comes from, and we set that equal to 5, which is the external secant the external segment on the bottom, times the whole secant length, which is X plus 5. Remember, we can't add those together because of the rules of combining like terms. So now all I can do is multiply the left side, which would be 90. Okay, on the right side I'm going to get 25 plus 5X. Okay, like that. And now it's just a matter of moving things around. So I subtract 25 over to the other side, and I get 65. So I get 65 equals 5X, and divide 65 by 5, and I get that X equals 13. So just try to look at the notes there and try to visualize what it is they did there. And remember, it's the external part times the whole length equal to the external part times the whole length. Okay? Part times full equals part times full. So here we are again. Now this gets a little bit more complicated because now we're on the bottom part there. We're going to have a binomial product. So the top one is part times full. So it's 3 times 3 plus x plus 2, which becomes 3 times x plus 5. And then on the bottom, you're going to have x plus 1 times x plus 1 plus x minus 1. So it's going to look a little bit like this. So there it is. On the top part, it's 3, which is the external, times 3 plus x plus 2, which is the whole length of the secant on the top. Then we go down to the one that's kind of on the angle at the bottom there. The outside piece is x plus 1 times the whole secant, which would be x plus 1 plus x minus 1. So now a little bit of distribution and combining like terms, and you're gonna be left with 3x plus 15 on the left and 2x squared plus 2x on the right. Now the reason why it works out to just be 2x squared plus 2x on the right is because if you look at that second set of parentheses and the step above it, the positive one and the negative one cancel each other out, so all you really have is 2x times x plus 1. Anyway, so now it's just a matter of moving some things around. But now this time, okay, your x squareds are not going to cancel out like on the previous slide, so factoring kind of comes into play here. So we end up with this right here. 0 equals 2x squared minus x minus 15. Now this gets really kind of complicated because now you got to go into the realm of guess and check to figure out what combination between 1 and 2 is going to multiply with the combination of 15 and then end up with a sum of negative 1 in the middle. So, we're going to do that here right now. So if you do 2x plus 5 times x minus 3, you can kind of factor that trinomial out there. And then now, since we have a zero product property here, we want to figure out, what our two possible answers could be. So if I was to set it up as x minus 3 equals 0 and 2x plus 5 equals 0, we get two possible answers of negative 5 over 2 or positive 3, and we only want the positive distance here in algebra or in geometry, so we leave the answer as x equals 3. Now this is a pretty complicated problem, especially that quadratic of 0 equals 2x squared minus x minus 15. So that's one we may have to discuss in class just to show you guys how to properly factor that down, but you got to use your rules of guess and check that we taught you guys last year in Algebra 1. Okay? Alright, so moving right along here. Now, Theorem 10.16, segments of secants and tangents theorem. So now you're going to have a possibility here where you have a secant like the one on the top part of this diagram, and then a tangent like the one on the bottom there. Okay, so it's part tangent, part secant. So the formula is you take the tangent and you square it, and then you set it equal to the external segment times the whole full segment, like it's, times the full secant. So just like on the previous, except now it's part tangent and part secant. So when you set it up, you're going to have 7 squared equals 5 times x plus 5, or 5 plus x in this PowerPoint. Okay, so now it's just a matter of simplifying. So 7 squared is 49 equals 25 plus 5x, minus things around. So 49 minus 25 is going to be, 24, and then 24 divided by 5 leaves you with 24 over 5 as the distance of x. Okay? Now, they do get more complicated. So on this one right here, now the tangent is x plus 4. So you're going to have x plus 4 squared equals, okay, x times x plus 12. All right? Now, x plus 4 squared becomes a trinomial square when you multiply it out. So you're going to get x squared plus 8x, okay, plus 16 equals x squared plus 12x, which is kind of nice because now your x squared is going to cancel out when you start to move things around. Okay, so you get 16 equals 4x divided by 4, and x equals 4. Alright, and now for the last one. So on this one right here, they want you to figure out the two other sides of that right triangle there. So we want to figure out what QR is, and we want to figure out what PQ is. Okay, so now all we want to do here is we want to start to use that tangent rule. So we're going to use the tangent and the secant rule. So we're going to take QR and we're going to square it, and we're going to set that equal to 14 14 times 14 plus 12. Okay, so you start to do the work here. 14 plus 12 is 26. 26 times 14 gives you QR squared equals 364. Now to undo squared, we're going to square root. And so when I square root both sides of that, I get 2 root 19. Alright, so now that we know that QR is 2 root 91, we can use Pythagorean's theorem to kind of figure out what QP would be. So all I have to do now is, there's my 2 root 91 for QR, so I can take that, plug it into Pythagorean theorem, which would be a squared plus b squared equals c squared. I know c and I know a or b, doesn't matter which one you say is which. Okay, so I plug it into that, so PQ squared, which would be a or b, plus 2 root 91 squared will equal 26 squared for the Pythagorean theorem. Alright, so now all you got to do is minus the 2 root 91, or square everything, okay, and so you get PQ squared plus 364 equals 676, minus the 364 over to the other side and square root that. Okay, so you get PQ squared is 312, square root it now, and you get PQ is approximately 17.7, or if you keep it in radical form, 2 root 78. Okay, and that's about it.